Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman, and I'm the Marketing Director here at the Academy. Today's webinar is titled From Flood Zone to Future Proof, California's first MBR-IPR mainline facility. Our Executive Director, Dr. Daniel Uther, will serve as the moderator and will introduce our speakers today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We will do our best to address each question at the end of the presentation. Before we get started, Dr. Uther would like to say a few words. Dan, how are you doing?
Hey, greetings everyone. Greetings, Marissa. Thanks for that introduction and welcome everybody to today's webinar. Today we have a very special presentation from the winner of the 2025 Superior Achievement Prize for our annual Excellence in Environmental Engineering and Science competition. Begun way back in 1989, each year the Academy invites our members to submit their best projects, from design to implementation, from university research to small systems, from planning to industrial practice, and everything in between. These projects are judged by an independent panel, and winners are selected for honor awards and grand prizes, and each year the Academy selects a single superior prize from among all of the projects submitted. And in 2025, that prize went to Black Veatch for the project that we're learning about today. So we have an amazing webinar planned for you today. Before I introduce our speakers, I'd like to take a moment to share with you a little bit about the Academy's Patrons program. Patrons are organizations who financially support the work of the Academy. They help bring our programming to you, our members, for free and reduced cost. When you speak with someone who's employed with one of the organizations on the slide, our 2025 patrons, I encourage you to pause and take time to say thank you. Offer them a thanks for their commitment to your success and their commitment to the success of the future generations of environmental engineers and science students who will care for human welfare and promote the health of the planet we all share. I note that Black Veatch is included on the slide, and I'd like to specifically offer a special thank you to Black Veatch for always being an exceptional patron of the Academy. Second is I want to make sure that you're aware that the Academy is currently soliciting projects for the 2026 Excellence in Environmental Engineering and Science competition. With a firm deadline of December 31, 2025, just 2 months from now, the projects that are submitted over the next couple of months will be judged by an independent panel of experts who will select our honor and grand prize and superior achievement awards. And those winners will be recognized at our annual convocation and celebration of excellence in Washington, D.C. in mid-April of 2026. So let us know about your best work. Submit to the E3S competition before the end of this year. As I mentioned earlier, it's my privilege to introduce some exceptional folks from Black Veatch, a longtime patron of the Academy and winner of the 2025 Superior Achievement Award from the E3S competition. Katie Zusi is a project manager and professional civil engineer at Black Veatch. She graduated from UC Irvine with a bachelor's degree in civil engineering. She's been at Black Veatch for over 13 years and has worked on the planning, design, and construction for various wastewater treatment and water reuse facilities throughout California, for plants ranging in size from 1 million gallons to over 200 million gallons per day. In her spare time, Katie enjoys skiing, hiking, reading, and playing on the Black Veatch softball team. Eric Bevington is a licensed professional engineer and DBIA certified design build professional with 24 years of experience in the water and wastewater treatment fields. Since earning his Bachelor's of Science in Civil Engineering from Arizona State, Eric has designed or managed the design of nearly $2 billion of water and wastewater infrastructure. He moved to the San Francisco Bay Area in 2011, where his career is focused primarily on wastewater treatment plants, including 3 advanced wastewater purification centers for indirect potable reuse. One of those projects was the Morro Bay Wastewater Resource Center design build project, for which Eric served as the engineering manager and engineer of record. Eric serves as the Director of Design Build Engineering and Design Build Solution Manager for Black Veatch. And fun fact, early on when he was an intern at Walt Disney, he managed to stall the blue monorail as it came out of Epcot Center. This was one of the fun facts we learned while we were in the green room. Eric, we may get around to asking you more about that when we get to the Q&A end. Colleagues, as a reminder, while Katie and Eric deliver their presentation, from flood zone to future-proof, California's first MBR-IPR mainline facility. Please place your questions in the Q&A panel so that I can use them to direct today's discussion. And now, Eric, I will remind you, it shows that you're doing screen sharing, but we don't see your slides, so maybe
let me try it again.
And now with those instructions to Eric about the slides and to colleagues about your Q&A in the panel, Katie and Eric, my friend, the stage is yours. We're excited to hear from you.
How about now? Are you seeing it now?
Not yet, my friend.
How about now?
Started screen sharing. Oh, there we got it.
All right, we did
We're
it.
golden. Eric, over to you. Katie, over to you.
Where do I get the laser pointer in this mode? Well, if I move my cursor, can you see that?
Yes, I can.
Okay, perfect. I'll point to stuff that way. All right. Well, we're excited to talk to you about our Morro Bay project. This is a project that Katie and I worked on for, gosh, what, about 7 years? And we're very excited to share it with you today. So this is actually a picture of Morro Bay. It's a beautiful place to deliver a project. It's in the central coast of California. I call it California before all the people ruined it. So pristine ranch land, large rolling hills, pristine coastline. It's an absolutely beautiful place in the world. So our agenda today, first we'll take you through the project drivers, why Morro Bay did this project. We'll go into the final product since it's done and been operating now for 3 years almost. We'll show you what it looks like, and then we'll get into the design features and how it works. And then I'll talk about fixed price design build delivery. This project is unique. It was delivered by fixed price design build, and then a little bit about the current operation. So one of the key driver for the project was California's Coastal Commission denied Morro Bay's permit to continue operating their existing 7-year-old wastewater treatment plant right on the coast next to Morro Rock, right on the beach. The primary concern being flooding with sea level rise and also climate change. So Morro Bay needed to find a way to take the plant to high ground. And this is very important for them because their main economy in Morro Bay is tourism and fishing. So you can imagine the disaster it would be if they lost their wastewater treatment plant in that scenario. The existing trickling filter plant was 7 years old. It was, past its service life and needing a lot of work. And another kind of unique feature was creating a locally sustainable potable water source. Morro Bay is 100% dependent on imported water from the California State Water Project. And in severe drought, which we had around the beginning of this project, their flows from that system are greatly reduced. So this creates a local source of water where they're replenishing their aquifers so they can draft into that in drought periods. So on the left here is the old wastewater treatment plant. Bring your beach chairs, set up your umbrellas. It is literally right on the beach. There's some trailer parks here for people visiting to, camp out on the beach and stuff. It's a really, really neat spot to have a wastewater plant. It's also right next to Morro Creek, a little foreshadowing on that. It got moved about 2 miles inland to this pristine ranch land, grassy ranch land. What an absolutely beautiful site. That took it uphill, it took it away from the flooding potential risk, but it also did make for a more complicated program. So this is the program elements for the Our Water program is what they called it. The most expensive and largest component was the Water Resources Center. That's the scope that Black Veatch and Filanc did as a joint venture under design build delivery method. There was another contract for the pipelines to bring the, where is it? It must be right in here. Bring the wastewater from the old plant. Oh, sorry, it's here. Old plant up to the new plant, and then the effluent back to the outfall at the old plant. They're going to continue using the old outfall, and the injection well field, which is being built around the same area. Okay, so let's talk about the end product. It's a beautiful site. You'll see what I'm talking about in a second. It's actually 2 plants in one, so double the fun. And process diagrams can be moving. So here's our beautiful plant site. Without a doubt, the prettiest wastewater plant site I've worked on. Usually they're in the worst part of town, surrounded by industrial parks. And so Our neighbors were cows and ranch land. It's absolutely beautiful. You can see the Pacific Ocean here in the background. There's Morro Rock. It's kind of famous icon, and the power plant stacks, which are also an icon, which I understand they are going to take down. This is the plant. It's kind of a long, sprawling plant. We'll talk about why in a little bit. The wastewater component of the plant is up here. So you've got your headworks, your BNR and MBR, solids handling, and our safe filtration system. We'll tell you what the heck that is in a minute. And this portion of the plant is the indirect potable reuse portion of the plant. So here we've got the RO-UV-AOP system in this building, our calcite contactor tanks to buffer the water, our product water tank to chlorinate the water, and then our outfall pumping systems are here to pump either to the ocean or to pump to the injection well field. These labels here are the various buildings on the site. So they've got a maintenance building up here. All the chemicals are centralized out of a central chemical feed facility. In the middle is a corporation yard. They run their entire water and wastewater system out of this one facility now. So they have got all their equipment and stockpiles of rock and all that stuff here. Storage for flow meters and all those things in the operations building. They've relocated all of their water and wastewater staff to this building to run it out of here. Okay, so we're going to do a flyover video. It's probably going to be a little jittery on your end due to screen share, but hopefully you'll get the sense of it. So here's at the front of the plant, looking north. That's the operations building in the foreground. We match the kind of farm ranch style buildings in the area. So that's why they have this kind of red roof look to them. Here's the corporation yard area in the middle of the plant. Behind it, you can see the product water storage tank, and the building directly behind that's where the RO and UV-AOP systems are. And here's our outfall pumping systems. Chemical facilities on the right there, maintenance building. At the back of the plant here is the wastewater treatment plant component of it. In the foreground is that safe filter that we're talking about. On the left here is solids handling. We're flying over the membrane bioreactor now and the BNR tanks. This was filmed during testing, so you can see the water is nice and not brown. And then headworks here at the top of the plant. Hopefully that showed up okay on your end. Okay, so here's the two plants in one. The mainstream is a traditional wastewater treatment plant using membrane bioreactor technology. So it goes through biological nutrient reduction with a membrane bioreactor on it. That's capped at 1.88 MGD, and that is one of our innovations that made this project feasible. You can see the peak hour flow is 8.14 MGD. So they have quite a large peaking factor due to a couple things. One is infiltration. Some of their sewer lines are actually below sea level along the coast, so they get a lot of infiltration, especially in high sea events. And then also it's a huge tourism destination, so their population will greatly increase overnight on a holiday weekend. So that also impacts these large peaking factors. The annual average is less than one, a little bit less than 1.97 MGD. So that main wastewater process, BNR, MBR, outfall chlorine contactor, and then it's pumped to the existing ocean outfall a couple miles away. Any flows above 1.88 MGD are diverted to the safe filter system. It stands for Stormwater Adaptive Filtration Equipment. It was a marketing name for a system that's really just a cloth primary filtration filter. So that takes any of these peak flows, and that allowed a lot of cost savings, which we'll get into a bit. So that's the main stream. The secondary plant is the IPR plant, and here we have RO, UV-AOP, buffering and chlorination, and then it's pumped to the injection wells, also a couple miles off site. On a normal day, the flow stream will be from headworks through this IPR. They won't be sending any water to the ocean outfall other than brine discharge from the RO system. And then flows above that average day start diverting more and more to the ocean outfall. Or if this system needs to be taken offline, they can divert everything to the ocean outfall. So you can see it has really great performance, and that's the beauty of membrane bioreactor. I am a huge fan of these things now after this project. BOD coming off the membrane bioreactor main wastewater stream is 2 to 5 milligrams per liter. Their regulation is 20. Total nitrogen, we're in the 2 to 4 range, regulation 20, and then turbidity is at 0.1 NTU, down from the regulation of 20. So really a big improvement on the wastewater quality. Okay, so here's the process flow diagram out of our drawing set, but why have a boring process flow diagram when you can have a fun one? So this is our process flow diagram from our proposal, and we used it in our BDR as well. You'll notice the cows. This is why it's moving. Cows were always on the site when we were there, and we noticed that, every time we go check out the site at the beginning of the project, the cows would come over and check out what we were doing. So the cows made it into our proposal here. You can see there's a lot going on, so I'm going to break this down into those two plants that I'm talking about. This is the main wastewater process. So you can see we've got at the headworks, core screens and grit removal. That's a package system. Here's the safe box. This is where flows above the 1.88 divert and go to the safe settle system and safe filtration system. Followed up by fine screens into the biological nutrient reduction aeration basins, and then the membrane bioreactor. That permeate then is pumped into the RO feed tanks. When those tanks fill up, so anything not used by the IPR system overflows passively to the outfall balancing tank over here, and it is then pumped into the chlorine contact pipeline and then off site to the ocean outfall. The IPR treatment process starts at the membrane bioreactor and those RO feed tanks. So you can see here the pipe actually comes off the bottom. So the IPR system gets its choice, first pick of the water coming off the membrane bioreactor. Anything above what it takes just automatically diverts to the ocean. So we actually flow by gravity from the RO feed tanks to the high pressure RO feed pumps, and we put the cartridge filters downstream of the RO high pressure feed pumps. That's unique. That's not typically the way it's done. We'll get into why in a little bit. It's a two-stage RO system with an interstage booster for added control energy savings. And then after the RO, we go into UV AOP. It's ultraviolet advanced oxidation process using chlorine, sodium hypochlorite, which also is a little bit of divergence from what has been the typical using peroxide. From there, we're missing it on this diagram is the calcite contactor tanks. That is to add buffering into the water because of, ultra pure water is actually very aggressive and corrosive. And then the product water storage tank where it gets a dose of chlorine to get some added log removal credits, and then it's pumped offsite to the injection well field. Okay, Katie.
Thanks, Eric. So now we're going to walk through a little more detail on the design features for each of these areas. So next slide, please. So first of all, talk about the headworks. Eric already kind of mentioned, but we essentially have at the head of the plant some coarse screens, vortex grit removal, the safe box, and fine screens. Next. So over on the left here, and we have this for all of our drawing sets, but we have this kind of 3D rendering before you dive into all the mechanical process sheets. It kind of helps you to visualize what it really should look like rather than just looking at those 2D plan and section cuts on the drawings. So we have over on the, let's look at the bottom one. You see kind of those big gray units. Those are the packaged headworks facility. The photos actually up on the top right as well. But this headworks, each one can treat 8.14 million gallons a day. So we have a duty standby system. They have 1/4-inch bar screens and the vortex grit removal all built onto these skids. We actually did, Eric's going to talk about the process and how we selected this unit, but one of the key drivers was that we actually determined from design through construction, it would be more cost effective to have these skids delivered to the site rather than to do a pour in place concrete headworks. And then also part of this area is the fine screen system. We've got 2 screens that treat up to 1.88 million gallons per day. Again, it's a duty standby, 1 millimeter openings. And the key reason we have these fine screens is requirement upstream of the membrane bioreactor to protect those membranes so you don't get any large materials or anything that can damage the membranes. Right, next we'll talk about the VNR and MBR system, so the aeration tanks. So these are downstream of the fine screens. You'll see on that perspective view, that top section up there, the flow is actually fed into the head of those tanks from the fine screens. And we've got 2 different trains, and each train has an anoxic zone and they're followed by an aerobic zone. It is designed so that during like the summer months when the flows are maybe slightly lower, that you can take a train offline and do some maintenance work. But we have those 2 trains, and then from there it is pumped up into the MBR system. The reason we're actually pumping into the MBR, I think more typically you would go by gravity from the aeration tanks into the MBR cassettes. But we actually, the city wanted us to build in some equalization into the aeration basin. So there's actually 36,000 gallons of equalization volume in those basins. So if they do get a slightly higher flow going into the BNR, they have a little bit of buffer space to kind of ride out some of those different diurnal flows. In the MBR trains, again, we have 2 cassette tanks sized the same as the aerobic basins to treat maximum redundancy. And then from the MBR cassette tanks, we have pumps that will pump the RAS back to the, RAS flows by gravity back to the head of the aeration tanks. Yeah. We'll pump the effluents into the RO feed tanks. And then the other nice thing about the MBR system is that it is the microfiltration for the indirect potable reuse facility. We also have a bunch of other equipment laid out in this area. We've got the blowers for the aeration tanks. We've got the air scour blowers for MBR. We've got the WAS pumps. We also have a 3-water system that the plant uses for their plant water and for irrigation purposes. So it's all kind of in this one area.
Oh, it's actually over here. Yep.
Yeah. All right, so the next piece that's kind of in between whatever is not treated by the biological treatment system is it actually gets sent through this safe box to another tank, which we named the safe settling tank. It's kind of an equalization tank that will take any of that excess flow, and it can hold most of those events when we go above that 1.88 million gallons per day. And from there, it flows through to the safe filtration system. Okay, so again, we have kind of our perspective view. This drawing actually has the solids handling and the filtration all in one area. But you can see on the far left, that's our filter system. We've got the photo of it, or 2 photos of it on the right-hand side. But this is just the one system. This one unit treats up to 6.26 million gallons per day. We have the one train. Again, it's not used very often, so plenty of time to do maintenance during those typical flow periods. This filtration system actually produces a much higher quality effluent than typical primary clarifiers. And then the effluent from this filter, when it does get used, it'll be sent to a tank that blends with the MBR effluents, and then it's disinfected and sent out to the ocean. Right, and then the last piece of that mainstream wastewater treatment plant is the disinfection and ocean outfall. I just mentioned the outfall tank where the filters and the MBR effluent combine. From there, we pump through a pipeline where we add sodium hypochlorite, and it goes through a contactor and out to the ocean. All right, so here's some cool photos. Eric and I were talking about it this morning. I have a really cool photo of him actually standing in front of that huge pipe in the ground. Eric's really tall, and the pipe is taller than him. I should have added it in here. But we have this whole long site that you saw from the fly through. So rather than building a storage tank to get that chlorine contact time, we actually did a value engineering exercise very early on before we even submitted our proposal and determined that we wanted to use this pipeline. It's a 72-inch diameter pipe, and it has that contact time. It also actually gets a much better baffling factor than a tank, so it's a lot more efficient use of space. And it travels through the site, and then from there it goes out to the ocean. I guess right ahead of that chlorine contact pipeline, we have this outfall tank. We joke and call it the octopus tank. There's all these pipes crawling into it. That's the MBR effluent. It's the filter effluent. Another thing we haven't talked about yet is all of the indirect potable reuse pipelines. So anything that needs to be diverted, if it's not meeting the water quality standards, or anything during startup of the potable reuse system, those pipes all go into the same tank. Obviously the water is completely treated and high quality to meet the ocean discharge, so it goes into there, and then from there we pump and we add the sodium hypochlorite, and it gets that disinfection through that long contactor. Right, and then the other piece of the main wastewater treatment process is the solids handling. Morro Bay is a very small facility, so they just send their waste activated sludge. They have a couple of sludge holding tanks that have some coarse bubble diffusers in there, and it gives them a lot of equalization volume, and from there they pump through to their belt filter press where They dewater the solids, and the solids are hauled off site. So again, back to this same area, you'll see the big concrete tanks at the solids handling facility. They've got 2 of them, so that likely they can just operate one at a time while they clean the other one. But they'll fill that with their sludge. They can cycle the air on and off. There's mixers in there just so that we keep it from going septic. We also have a large belt filter press. It's a 2-meter belt filter press. They only have 1 of them. The idea was that the city only wanted to operate it 2 days a week. So we have that set up so that they can keep their operations a little bit more minimal. And if the dewatered solids get down to 18%, and they get hauled off site to landfill. All right, so the last piece of the puzzle is this indirect potable reuse treatment train. We already talked about a little bit, and I guess it should kind of be highlighted, but the membrane bioreactor is actually a key part of this indirect potable reuse. Typically upstream of the RO system, you have to have membrane filtration. So the MBR actually doubles as both for this project. So from the RO feed tanks, like Eric mentioned, water will flow by gravity out of the bottom of those tanks straight down to the RO system. So typically you'll have multiple different pumps to pump through cartridge filters and then the RO. But since we have this hilly site, we actually just have 1 pump station that feeds the MBR effluent through cartridge filters and straight through the stage 1 of the RO. And then we pump through stage 2, and then from there it goes through the UV-AOP system. Right, so here's a photo of the building. There's a lot of pipes, a lot of things happening for anyone familiar with RO. You've got all of your chemical clean in place systems, your influent piping, effluent piping, any diversion piping, off-spec water. So there's a lot of stuff happening in there. And so we have 3 RO skids for a total of 0.97 million gallons per day. That number is actually the number that the City of Morro Bay wanted to be able to produce for their groundwater injection wells. So we sized the system to meet those numbers. Each train does about 1/3 of a million gallon a day each. And each train is 2-stage RO. I already mentioned that it does flow by gravity from the RO feed tanks straight to those pumps. There's a cartridge filter on the high pressure side of the pumps, and then between each stage, we've got that booster pump. Then from the RO skids, we have 1 UV-AOP train. You'll notice it's 0.82 MGD. It's a little bit lower because of all of that RO concentrate that gets sent out of the RO and does not make it through to the clean side. So the number is actually lower for the UV-AOP system. And one other unique thing is that we're using UV chlorine. The city did not want to have another chemical on site by doing peroxide. So we are using UV chlorine. Right. And then after the IPR treatment train system, we've got the buffering and chlorination. So in this area, we've got calcite contactors. So we go straight from the UV-AOP system through the calcite contactors. There's 2 tanks, and it gives them about a 6-month media life. And those calcite chips really provide that buffer to help clean up the water so that's not overly aggressive when it goes through those pipelines and into the storage tank. Then we also have the product water storage tank. It's 200,000 gallons. Part of that tank is used for chlorine contact, and the other part is equalization volume. For anyone familiar with indirect potable reuse, you need to have a certain log removal value for Giardia, Cryptosporidium, and virus. And so in order to meet those different removals, you sometimes will need to have a little bit of extra steps in there. So one of them is this chlorine contact. It gives the city a little more flexibility to help achieve that. All right, so with that, I'm going to hand it back to Eric to talk about the design, build, delivery method that we use for this project.
Okay, thanks. Okay, so like I mentioned earlier, this project was unique in that it was delivered by fixed price design build. And I'll get into a little bit about what that means here and how that compares to kind of a traditional design bid build delivery method that everyone's probably familiar with. I'll show you the project schedule and how that schedule compares to a traditional design bid build delivery method. We had 10 weeks to design an $80 million super complicated plant. So I'll show you what that looked like. I'll walk you through some of the innovations we came up with to reach the lowest price, even though we had the most expensive process by putting in an MBR, and still are able to win the bid with the lowest price with that expensive process. And I'll show you that collaboration is actually still possible with fixed price design build. Okay, so for those aren't familiar with these delivery methods, on the left is a traditional delivery method contracting structure, which also applies to CMAR or CMGC. The owner holds contracts with the engineer and the contractor separately. And that means coordination between those two parties has to go through the owner, and through Spear and Doctrine, the scope and gap risk is held by the owner. So if the engineer misses something on the drawing, the owner is on the hook to pay for the contractor to add it, and vice versa. So that is the kind of traditional structure. CMAR and CMGC, which really are the same thing, modify that a little bit by bringing the contractor on early and having some coordination directly between the two of them, but it's still contractually it's the same general structure. Design build is different, where the owner holds a contract with a single design build entity. That entity has the engineer and contractor within it. That can be a joint venture, like in this case, we were in a joint venture with Filanc. Or that can be a single entity that does both. Black Veatch is one of the companies that's capable of doing that, as along with others. Or that can be a prime sub arrangement where either the engineer or the contractor or the prime. Here, the main difference is the scope and gap risk gets moved into the design build entity. So it's a lot more risk control for the owner. These bars over here kind of show the difference relative to design bid build traditional delivery. So that's kind of the middle of these bars on how things, the different levers and how they apply with this fixed price design build delivery method. You can see the key owner benefits and reasons why they would choose this, and the reasons why Morro Bay chose it is better risk control, better cost certainty and clarity, and maximize potential for cost savings. And that really was a big deal for them. Morro Bay is not a big city. It's only 10,000 people paying for an $80 million plant, plus another, a couple $100 million worth of pipeline and stuff. So they really took on a big project here. This is the schedule for the delivery of the project. The SOQ was issued, I think it was Q3 of 2017. The shortlisted firms were invited to submit a fixed price proposal. A lot goes into that. I'll show you what that is. And then when the project kicked off in, I believe it was October of 18, we went then from 30% to IFC design, which is issued for construction. It's 100% design set. And then construction phase was a little over 2 years. The gap here actually was due to a site access restriction with the land purchase that was going on between the city and the rancher. That's why there's a little bit of a gap there. Then into startup, permitting, and the IPR startup. You can see here storm. I'll tell you what the storm is about later. So this is how the schedule compares to what it would have been if it was a traditional delivery. Key benefit of design build is it does allow you to compress the schedule. So this probably pulled the schedule back about 9 to 12 months. And the reason for that is a lot of this design is moved up into the procurement phase with that proposal. And it's also streamlined. It also allows you to overlap design activities and procurement activities, which we did do because we were procuring equipment even though we were in design. So that's the reason for the difference. Here's that stock up on your caffeine fixed price design build proposal, and I'll expand that and show you what that looked like. So that little bar was about 5 months. This is what it looked like between November of 17 to June of 18. Here's this 5 months. So the RFP was actually issued, I think it was January 11th of 2018. And the bid was due May 18th of 2018, if I recall correctly. We actually started work before, and you really have to on these things. There's just not enough time in those 5 months to do everything you need to do on a fixed price bid, because this is a binding bid. They could say, you're hired, build it, here's the check, call us when you're done, and that's it. So we started with, it was in actually probably October, with process designs and ideas. This is where we germinated the idea of the safe tank and some other ideas, safe filter system, I'm sorry. We had a workshop where we vetted through those and figured out which ones we're going to carry and advance further. And then we did alternatives design pre-work. We didn't know what exactly they were going to be asking for. We had an idea, but so we had to do all this in kind of a guessing state. Then the RFP was issued. Now we knew exactly what we were responding to. They gave us a technical requirements document that had what they were looking for and level of quality, what kind of features they were looking for, and we were able to adjust our approach. So we had a little under a month to prepare for a design charrette. And this design charrette was a very expensive and very productive meeting. There were about 50 people in the room for 3 days, representing executive management of both companies, cost estimators, procurement, design, construction, finance, administration, all of it. Everyone was in the room. And I drove the poor team really hard to come up with multiple designs for everything. I think Katie came up with 3 or 4 different designs for the BNR system. We had different treatment technologies. We had sequencing batch reactor. We even looked at an ox ditch, and then membrane bioreactor. And in that meeting, we were able to actually on live do cost estimates and determine which options made the most sense, the pros and cons and trade-offs to shape what our proposal was going to look like and what we thought would give us the best chance of winning on a low cost basis. So after that charrette, we knew what we were designing, and this is where we had 10 weeks to prepare bid documents. And these are documents that are issued out to vendors and contractors for earthwork and all that, just as if it was an actual bid. So we had a period of time here preparing basically a 30% design, went through an internal value engineering workshop where we tightened the belt a little bit, came up with some of those ideas Katie talked about, like eliminating those pumps and that pipeline, I believe we came up with in that workshop as well, and then took it to the 30 to 50% level. Now this is kind of a variable level on a design build on this fixed price because you're really trying to capture cost. So the P&IDs, process and instrumentation diagram, drawings, those things were darn near 100% complete. They control the scope of the job. They show us every instrument. I think there's 1,500 instruments on this plant. That was all in those. Other stuff that's expensive, like structural, process mechanical equipment, all of that was probably the 50 plus, maybe even 60% design level. Stuff that is easier to carry a cost for, like pipe supports, yard details, paving details, those things. That was at probably less than 30% completion level. So in addition to that, we were preparing bid packages for all these things with specifications, full specifications. All that was issued out for it bidding. Got multiple bids back from everything. You have to then do a comparison process and do bid alts where you do add alts and deductions on each scope to adjust everyone to the same apples to apples comparison, figure out which bid you're going to carry, and then bid close where you go through every single item, figure out what you're carrying, all your assumptions, risks, all those things. So it's a very busy process. It was the hardest thing I've done in my career, also the funnest thing I've done in my career. It was kind of like those college projects where you're up all night with your team and you think this sucks, and then you remember later that it was actually super fun. It's like that, but you actually get paid for it this time. Okay, so this is how we came up with giving them a membrane bioreactor. Our big, hairy, ostentatious goal was to give them an MBR for less than an SBR price, because we knew SBR was really the only way to win this on a low-cost basis unless you did something very different. So big cost saver was the SAFE system. That saved about $7 million. Where that savings came in was not building a large flow equalization basin ahead of the plant, along with other components. So that saved about $7 million. Another big savings was surfing the site. Photos don't really do it justice. These are big hills, and this plant is built on the side of basically a mountain. And a traditional approach would have had, a rectangular plant layout like we've all seen, and a lot of excavation work, huge retaining walls. We calculated it would be about 100,000 cubic yards of soil export we would have to do. So we came up with instead actually surfing the site. That's why the plant's all strung out in this long line following the contours of the existing site. And we use the site fall on that surf down the hill to drive the flow. So you can see the slope on here where we moved the flow between the processes by gravity rather than pumping. There's these pumps that Katie was talking about. We eliminated the low pressure transfer pumps you usually have to feed through the cartridge filters into the RO high pressure pumps. We ran by gravity. I'll tell you, that was the hydraulic calculation I was most terrified of. Poor Katie had to prove to me like 6 times that it was okay, because you can turn a pump up, you can replace a pump with a bigger pump. You can't turn gravity up, but it works, fortunately. And then omitting microfiltration by using the membrane bioreactor to do double duty saved another $4 million. This was the first mainline wastewater plant in California to be permitted for that. There's another plant that's a scalping plant that also does the same thing, that was slightly ahead of us on the permit, but this is the first actual mainline wastewater plant that does it. Okay, all right, we're doing okay on time. Collaboration is actually possible with fixed price design build if you select the right team and if you make it clear that's what you want to do. We knew Morro Bay wanted collaboration. They wanted the fixed price because they needed that cost certainty. They needed the lowest price possible, but they also wanted collaboration. They wanted to have input. So we ran the actual 30%. So this 30% was the bid set to issue for construction. We ran that like a typical design phase with the 60% submittal, 90% submittal, IFC, all the design meetings where we go through the pump station, all that stuff. The key difference is any options they wanted to look at or changes, we were able to come to them with the actual real cost impact of that and the actual schedule impact, whether it was an add or a deduct or if it was a wash. So they could make decisions on what they want to do with real numbers in mind. They could decide if they wanted to spend that $300,000 on centralizing the chemical facility. That was one of the decisions they made. Or if that $300,000 would be better spent somewhere else on something else that meant more to them and added more value to them. So it's a really good process. After that was done, then we updated the GMP, guarantee maximum price. So basically adjust our fixed price bid to everything, all incorporating all the changes, and then started construction. Okay, current operations. The plant now, the wastewater portion of the plant has been in operation for 3 years. I think 3 years, like last week, is when we seeded the plant, started operation. They have had no discharge violations from the first minute of startup. And for a biological wastewater treatment plant, that is pretty rare. So we're really proud of that. That is another testament to the strength of a membrane bioreactor technology. It really can do wonders for you. The IPR injection well field is under construction. I think it's going to be completed in 2026, mid 2026, and they'll start injecting into the aquifer at that point. Currently, they're running the IPR system, but they're taking the lovely product water and just putting it in the ocean outfall and sending it off to the ocean. That's to keep all the equipment exercised, keep the operators current on operations, all that stuff. Here's a comparison of the old plant versus the new plant. Old plant was a 7-year-old trickling filter, new plant. Turbidity coming off the old plant typically range between 20 and 30 NTU, sometimes higher. New plant, 0.1. BOD coming off the old plant, 10 to 15 milligrams per liter, often exceeding their permit of 20. New plant between 2 and 5. And total nitrogen, same thing, 15 to 20 or so on the nitrogen coming off the old plant, sometimes higher. They had discharge violations. New plant is in the 2 to 4 range. So significantly better water quality being sent to the ocean outfall. Okay, well, sometimes someday becomes today. So this plant was done to prevent the risk of someday in the far future, the old plant being flooded. Well, that far future turned out to be only 3 months after we started up the plant. Only 3 months. And on January 10th, 2023, they were hit with a 500+ year storm event. It was a state of emergency. Highway 1 was flooded under about 6 feet of water. No one could get out of the plant site. Everyone was trapped there for a couple days. And this is what the old plant looked like. So the old plant was flooded about 3 feet deep with mud and water. You can see this door here. The water line is about halfway up. This is a couple days later after the water drained off. Destroyed all of their electrical equipment, most of their mechanical process equipment. These are the intake screens. You can barely see the top of them poking out of the water. This must be a sample sink or something bobbing on the surface. If they had still been dependent on this plant, they would have had to have discharged raw wastewater to the ocean for months, if not over a year, to get all this fixed. This was, right after COVID. Equipment supply was a real issue. They would have been a real world of hurt. So kudos to Morro Bay for having the foresight to do this and get ahead of it. And boy, they were lucky. They got 3 months ahead of it. All right, well, that's it for our presentation. This photo I actually took at one of the public tours they ran. This was the, I think the grand opening tour. They have done an incredible job of running the public through this plant to show them this technology. This is a big advancement for that area. And this is the first of its kind. A lot of plants in California are on the coast. They're going to have to move inland, and they're going to have to look at similar technologies of this. So Morro Bay really was a front runner in this. I thought it was pretty amazing that there happened to be a rainbow out that day. So that's it for our presentation.
Love it. Thanks, Eric. Thanks, Katie. We really appreciate you. Eric, I'm going to ask if you pull down the slides, if you'll stop the screen share, and then that way people can see our smiling, happy faces so we can run through some of these questions. I know, Katie, we're going to end up losing you at some point in time through this, but we'll go ahead and get started. So we've got some questions that came in the background, trying to understand kind of like the site, right? Like the physical layout. You answered some of those as they came in, so it kind of helps some of those. But folks were kind of interested in, is it the new one in the floodplain or not? I think you answered that with the old one. So there were some questions that come in about the site, so we'll unpack some of those. Then there were some questions that came in around the space of collection and discharge, right? And so, thinking about the ocean outfall, was it moved? Is it the same one? Thinking about the aquifer, what are its characteristics for the indirect potable reuse? Where does the effluent from the safe process go? Does that just go to the outfall? How were those managed? And in particular, it seemed like you mentioned that some of the peak included some I&I, that maybe included some salt water. And so how does that salinity impact your operation if you've got some salt water coming in your I&I? So that's kind of on the collection discharge space. Then we had a number of questions that were kind of in the unit operations. And so we've got a lot of these that will kind of tick off. Folks were like, hey, we're looking at the influent characteristics. We're looking at the effluent characteristics. You've got this piece of equipment. Why did you select this one? Why did you select that one? So those are very like what you might think of as straightforward. I'll shoot them to you. We'll go through them one by one. You'll be able to, to answer them, like why this MBR, who was the manufacturer, why belt filter press instead of centrifuge, what's the recovery rate for the RO system? So they're kind of, straightforward engineering questions. So we'll knock those off one by one. Then there were some questions that come in this kind of policy guidance regulation space. So you're introducing this interesting way of project delivery. So folks were kind of curious to unpack and understand that a little bit. Were there compensations for folks who had started some of the design before even bidding had gone on and they had won things? Like how do you recoup some of that kind of lost leader idea when you're doing this kind of process? Contingencies for change, we're all familiar with those. So how does that get built into this kind of process? How about the NEPA and the site work and all that? Is that part of this or is that all done before? How do you manage that kind of, design build yourself? How do you manage the ethics of that? How do you manage the team on that? So now when you're taking on a lot of those risks and the owner doesn't have those risks, how do you manage that internally? So some folks wanted some questions in that to gain from your kind of like, best practice. One that was in there that, Katie had alluded to, but we'll talk about, is it like 2 permits, right? Is there like the NPDES permit for your wastewater? And then there is like your drinking water, Safe Drinking Water Act, surface water treatment rule, kind of like how does that fit in? Because a lot of us aren't in places like California where we've got these direct and indirect potable reuse. So how do you even leave your O&M folks behind where they've gone from operating a wastewater plant to now operating a high-tech water and wastewater plant? And it's all turnkey and you've given them all brand new stuff. So if you can speak to how do you manage that with a workforce that's maybe not accustomed to that. So you can design it as an engineer, but you're going to walk away and somebody's going to have to run this thing and run it 20 years from now. And so what training would students or new engineers want to pick up to be competent, to be able to work in this space? Because let's face it, this is somewhat a niche market relative to maybe how some people have historically been working across the U.S., but more and more people are starting to work this way. So, as a leader, we want to gain from your experience. So that's kind of the stuff that we'll walk through. I've got a few more that are coming in as we're going, but let's go back up and look at this site, right? So, all right. So the site layout's a little bit unusual. You talked through some of the fly through, and part of this might have already happened before you were there, or part might have been already what's going on, but you got an old spot, you're moving to a new spot. What happens with the land left over in the old spot? How did they acquire the new spot? How did this trade-off go? Is it out of the floodplain now? And how did you manage that? So if you can speak a little bit to helping us understand that site selection.
Sure. Okay, I'll take that one. So they had a lengthy site selection process, which was before they procured this design build to build the plant. So the selecting the site happened before we got involved. It was very political. It's an area where they do not want to become the next Los Angeles. So there's a large portion of the population that is opposed to anything that could support more growth. So that was a very complicated process they went through to get this site. Eventually, they ended up on this site. It is well above the floodplain. It's on the side of a hill. There is a creek running along it, at the bottom there, but the creek is, I think, 30 feet below our lowest point on our site. So it is zero danger of flooding, other than water coming at it from the top of the hill, which I was very concerned about in design. So I did the world's most robust drainage system, and it worked. It completely handled that 500-year flood. So the new plant suffered no damage during the 500-year flood. There was a portion of the ditch that got kind of undermined, but besides that, it was designed for a 100-year storm. It handled a 500-year storm. So you're asking other questions about, can you remind me some of the other questions you're asking on the site? Oh, the layout. Why?
About what happened to the old original site? How did that, and how was maybe was it a land swap, or what's going on with this? Because, we don't often get the opportunity to turnkey brand new site, brand new soil, brand new everything. So that's kind of really fun. And you only had 10 weeks to do it, right? So there's a lot of questions like, okay, so what happened to the old? How did you move the pipes back and forth? A little bit of the questions of the eminent domain. So it sounds like a lot of the site work in terms of where it was going to be or what was going to happen, the politics of that preceded you getting involved. So
where it was going to be, yes. But what we, took on was an empty site, grassy hills. So none of the earthwork or anything had been done. None of the plant configuration had been done. They had a conceptual layout, which had huge retaining walls and everything like you would expect. They retained the old site. It's being demolished. That was a separate contract to demolish that plant. The outfall collection box is on that site, and then the outfall pipeline leads from that side. That's in operation with the new plant flow going to it. Also, all of the wastewater flow, with the exception of a few lift stations, goes to that site as well. They're also collecting it and pumping it up to the new plant. So those components are at that old site. They've been elevated to be up above the flood risk. But all the rest of that plant's being demolished. And I think they're still deciding what to do with it. It's clearly a very valuable piece of land being right on the beach. So that's it for that. I think, did I answer all your questions on?
Feels like it. So this is completely out of the floodplain. You're not worried about anything in the future. And
they're high and dry.
The pumps and everything that's down there that's still at the old site, that stuff's been adjusted and removed. You know what? When the layout is very elegant along, taking advantage of the slope of the hill, blending in. Was that part of the work that you folks were doing as the design?
Yes.
What I might characterize as the aesthetic, or maybe a little bit more in the architect kind of flavor of it. Did they give you that, or did you actually decide that as part of
We did that. Everything you see, we came up with. The conceptual layout that they did issue with the RFP was very different. It was for an SBR plant, and it was a traditional kind of, rectangular layout that you'd expect to see, with a couple levels and huge retaining walls. So that layout, actually, one of our engineers, Kevin Lee, kind of came up with the idea of surfing it, and he did that layout. Then he moved on to other projects, and I inherited it. Actually, I did most of the site work myself, and boy, I wish I had made it about 5 feet wider. It was so hard to squeeze all those pipes and things in. And every time we're like, oh, we have to add another bypass pipe. I'm like, man, that 5 feet would be really handy right about now. Because you have to have a lot of, DDW, which is division of drinking water, spacings between different pipes, different flow streams. for protection of the public. So that really adds up. You've got to have 8 feet between raw water and potable water, things like that.
So that ate into your site plan quickly, I imagine.
Yeah, it sure did. But we did a unique approach. We put all the electrical on the west side of the site, and we did all the piping on the east side of the site. And the reason for that is construction sequencing. Electrical usually goes over everything else, but you need the electrical to be in place so you can run everything else, and you kind of get in a catch-22. So there were a lot of things we did with the design that were actually tailored to facilitate the construction, lower the cost, lower risk, improve the schedule. That's one of the powerful things about design, build, delivery, because you have both of those components being done at the same time. Makes the design a lot harder because you're thinking about things you normally don't think about in design, but it's also really fun because you're really kind of thinking ahead.
Thinking about things you don't normally think about.
Yeah, like when are you putting in your duct banks? Because you can't even start them till all the piping's in, but you can't get the pipe for another 8 months because it takes that long to get it, fabricated. So those kind of logistical arguments. So I was like, well, then let's put the electrical on the west and the piping on the east. And that's what we did.
Nice. So a little bit now, moving on to thinking about collection and discharge, right? So, okay, so what were some of the characteristics of the aquifer into which some of the indirect potable treated water was injected, right? Like who owns it, who uses it? Is it just kind of like, hey, it's California, let's hang on to our water as long as we can? Or is there actually somebody who is literally saying, no, I'm going to pump from that because there's also the drinking water facility that's there? Like, how is that being handled?
Katie, do you want to answer that, or do you want me to dig into it?
Yeah, I can start, then you can add on if you want. So the city actually owns the injection, not that exact location, but they actually use groundwater for their drinking water for parts of the year. It has to be supplemented by California Water Project, as Eric mentioned. And so doing part of this project is so that they can help make sure that they have more groundwater available during certain times of the year. So the city will actually own and operate those injection wells. I don't know that Eric and I know too much about the characteristics of the aquifer. That's actually another project, so done by another like hydrogeology firm. So I don't know about characteristics, but it will be owned and operated by the City of Morro Bay for their drinking water system.
Some general things I know about it. They did tracer tests. They need about 2 to 3 months detention time between injecting and drawing. That gives them some more log removal credits. So they've had to do testing to prove that was the case. One of their key concerns with the aquifer is seawater intrusion, which is a real problem in California and coastal cities. So the injection well field is actually between the ocean and their supply wells. So it, mounds the groundwater and prevents seawater from getting into their aquifer.
Awesome. So then along on the, so that's kind of a discharge side along the lines of the discharge, right? So they're using the existing outfall. Did they have to modify that in any way? They have to bring it further out? Because it seems like the SAFE system is essentially an elegant version of saying a stormwater bypass, right? And so with some treatment before you put it out there. So let's assume that we're not talking the elegant version of that. We're talking, like in the default mode, it runs out to the ocean. So did they have to make any changes for that as part of this permit, or were they able to basically continue to use the same infrastructure that was there?
It's the same infrastructure. They did an evaluation to determine its condition. It was still in serviceable condition. It didn't need to go any further out. In fact, the water quality is better than what they were discharging. The safe effluent, and Katie mentioned this when she was talking about it, blends with the MBR effluent. And that blended stream is what's discharged to the ocean. And that blended stream meets permit. Oh, there you go. Katie's got some.
Yeah, actually, we have this slide from another presentation that I just pulled up on the side.
Perfect.
But it shows that this is from modeling. I think ultimately it's much higher quality, but modeling is very conservative. But we modeled with the safe system in operation. So we looked at like worst case, we got that high flow coming in. We're producing IPR water, which means that water is going to the groundwater. We still have some going to the ocean. And we're also blending that safe effluent. That's this first column here. This is what the TSS VOD, which those are the key limits at the ocean discharge. That's what we have to meet. So when you're operating that filter and producing IPR water and sending to the ocean, this is what the water quality looks like. And I saw the comment too about the current plant or the old plant. I don't know the exact numbers, but I know that they were much higher than these numbers here.
Got it. No, thank you. Appreciate
Yeah,
that.
they were having several violations a year at the old plant.
And then how about, so you mentioned the I&I, the saltwater intrusion. So how about that in terms, so this is now on the collection side, right? So how does your biological system handle that you hit it with salt every so often?
For the most part, it really hasn't been an issue because it's diluted with a lot of stormwater. Because usually when the sea level is super high, it's during a storm event. And so you're also getting a lot of rainwater blended in. So salt really hasn't been a problem. The problem was flow. In that storm event, the plant was designed for 8.14 MGD. It saw, I think they were over 10 or 12 coming at it. It was designed for a total suspended solids of, I want to say it was like 250 or something like that. We had well over 1,000. It was liquid mud coming into the plant, and it still met discharge permit, which I'm super proud of. And it was only 3 months old at the time. So that pipeline, the one, it's their main street is right there on the bay, and that's the one that they think they get the most infiltration from. But if they tear it up, then they also lose their main income source. So it's kind of a catch-22. They're doing projects to try to reduce I&I, but that's an ongoing thing they're working on as well.
Awesome. Now we're going to move on to a few questions that focus on some unit operations. Katie, thanks for joining us. Eric, we're going to put you in the hot seat, but
all right. Bye, Katie.
Katie. So, okay. So a number of these came in, they're like specific questions from folks. So I'm not necessarily going to put them on the spot. I'm just going to read their questions so you're able to handle it. So
sure.
One question was that, influent BOD and nitrogen and solids come across as higher than typical municipal sewage. Can you explain that given the I&I that you mentioned? And does the final outfall have any specific effluent limitations? So if you could speak to that.
Yeah, and I'll do as best I can. I really would need one of our process engineers involved in it. They dig into the weeds on that stuff. The main driver for it is Morro Bay is it's a residential community and a tourism community. They do not have much industrial or commercial activity. So it's more concentrated wastewater flow than you would see in a typical city with a broader spectrum of uses. So that's why the BOD levels and things are higher than you would expect. Also due to water conservation, being that they are dependent on state water and it's a scarce supply. They push water conservation very hard. Their water rates are high. So there's a lot of incentive for people to minimize their water use, which makes it more concentrated as well. And that's a trend we're seeing all across California. We are getting less wastewater and it's more concentrated. So we're getting more nasty water, and now we're trying to make drinking water out of it. So it's a very dynamic environment to be doing this work in.
No, I get it. So we got a couple of questions, particularly on the MBR. So, why was the MBR selected? Advantages, disadvantages, other treatments that were there, and then the one you selected. Who's the manufacturer? What was the style? So, if you can tell us a little bit more about particularly the MBR alternatives and why this selection and this particular one.
One of the drivers with the MBR is we knew the plant superintendent really wanted a membrane bioreactor. We knew he was a big fan of that. And that's, in pre-positioning and knowing your client, what their preference was. But it's also, as kind of the data is proven, probably the most robust wastewater process to have really low turbidity and discharge levels because you've got that super tight membrane on there. Another big driver for it is it's a very low footprint technology. Your aeration basins are smaller because you're running at a higher mixed liquor suspension solids than you would on a typical BNR plant. And that allows you to reduce the footprint of that. Plus the MBR itself is tiny. And that's a big deal in California. That's why this is kind of the first of many. Land is at a premium in these coastal cities. You're going to see a lot of these MBRs popping up as plants have to redo their plants. So, their budget could afford an SBR, sequencing batch reactor. The size of the plant matches with the sequencing batch reactor, but they're like we talked about, the preference they had, the water quality improvement they had, and the footprint, although they had a large site, were kind of key drivers for it.
Makes sense.
Yeah.
All right. So then moving on to the solids. So why a belt filter press over a centrifuge? Any thoughts?
That comes down to the landfill.
Okay.
So,
where do solids go?
For hauling, yeah, and that's where you get into these things. Constraints are sometimes not what you would expect, but the only landfill they could find that would take the solids required them to be at least 16% or higher. And that was one of the guarantees that Morro Bay was asking for in their proposal. And the word guarantee is a strong word in the contracting world, right? That means if it doesn't work, it's on us to pay whatever it is to make it right. And so we could not find any manufacturers of centrifuges who would guarantee their equipment could achieve 16+%. But we could find belt filter press manufacturers who would do that. And that's why it's a belt filter press.
So the owner wanted the guarantees. So then you, as the design build, found a supplier that would, then you just pass the guarantee on, right? So
yeah,
okay.
yeah, that's basically what you do. And you know, because we didn't build the equipment, they did. But that's really what it is, driven by what the landfill required. Then Morro Bay said, well, I don't want to take that risk. I'm going to put that in the contract that the design builder has to take that risk. And then none of the centrifuge manufacturers would take that risk. So it's a belt press.
Yeah, makes sense. Makes sense. So now moving over a little bit more, thinking about some of the drinking water, the indirect potable, and that. So what's the recovery rate for the RO system? Was there a separate outfall for reject disposal to the ocean? Are there permitting challenges around that? So if you want to speak to that one a little bit.
So recovery rate for the RO system, it was designed to be able to run in a range between 80 and 85%. Above 85%, you're going to get into a lot of scaling issues. And it really just wasn't worth the cost, the capital and operational cost to make it more complicated to squeeze more water out of it. So I think they've been running at around 82 because it's the easiest place to run. But it was designed to run between 80 and 85% on the recovery. What were the other questions? I'm sorry, I was trying to take a note.
Permitting challenges.
Permitting challenges.
Where does that reject go? You know,
the reject goes to the ocean outfall. Another cost savings idea. Usually, you know, you would collect your brine or your reject into a tank, and then you would pump it. Well, those are expensive pumps. Those are, Hastelloy C or, what's it called? Duplex stainless steel pumps because of the concentration of the stuff in it. So we came up with using residual pressure from the RO system to actually push it directly into the outfall pipeline and skip pumping. And so that saved quite a lot of money and complexity on that. So it goes to the same ocean outfall as everything else. It all gets blended in that one pipe and out it goes. It has its own chlorine contact pipeline, and then it's added in after the main, that big 72-inch pipe.
Okay.
Because we needed to control chlorine contact separately between the two streams depending on what's going on with flow. So that's why it's got its own. It's a 12-inch contact pipeline. It's much lower flow.
Makes sense. Makes sense. All right. So now we're moving on to, AOP, alternatives to chlorination, reviewed and discussed. You want to speak to that one a little bit?
Yeah, boy, you want to talk about a complicated world. AOP is something else. This was my first time going through that. I've done UV before, but not AOP. Peroxide is the standard bearer. That's what everyone does. It comes with some cons. It's expensive. It's a flammable chemical. So you've got some really expensive chemical facility design features that you have as a result of using it. And then you need to quench it afterward, which is another process and another cost. So UV chlorine, at the time we were designing this and bidding this, was a new thing. I think only a couple plants had been doing it in California, and they had some challenges with it because it comes with its own complexities. Was a boron and things like that. So you can get some reactions that can make some other things that get you in trouble the other way. It's cheaper. UV chlorine is cheaper. There's some synergy because you're using chlorine in your plant anyway. But it was a tricky design, and it was tricky to do the chlorine inventory to make sure that we were in compliance with our discharge regulations. So it seems more and more plants are going UV chlorine. It does make a lot of sense. It's tricky in different ways. So either way you go, it's complicated with UV AOP. You would think it's just some bright UV light bulbs and add a little oxidant in there and you're done. But oh boy, no, it is. And the permitting is very complicated on it.
Well,
very complicated.
The engineer of record on this whole thing, right? Like you've got to go all the way. Like it's not just a wastewater plant. It's not just a water plant. You've got to, I'm putting you through your paces with these questions because
yeah, that's fine. Do it. And if you want to get into the speciation, that's where I'm going to need a process engineer to come in because I'm like, you just tell me how much chlorine we need to feed in this thing, and I will get the people to design the pumps. You
Fair
can
enough.
talk about your species of chlorine. So
Yeah, fair enough. Fair enough. Okay, no, fair enough. So, okay, so then a little bit then more about, the safe so is the design to default to the outfall? I mean, is that essentially the way the system is set up that, that in default mode, it would just simply, it would just go to the outfall and otherwise you've got it operating. So we're just thinking about protecting the groundwater supply. So I imagine the default is not to the groundwater. The default is in fail mode, it would just go to the outfall as opposed
yeah.
to potentially contaminate that groundwater. All right. And so then another question about kind of like the safety is it felt like there was there's some hydraulic buffering in that safe system, right? But it's a safe system. It's already for a system that's skirting your main, kind of feels almost like belt and suspenders kind of, right? So it seemed like from Katie's presentation, like, well, the city wanted this extra buffer capacity in there. How did that work? I mean, how many of these you've assumed all the risk because you're doing the design build. So then how much do you have to listen for? They wanted a little extra safety in there. Do you have to take that on board, or is it just kind of, does it make sense to take on people's, if they want extra safety, you build it in because they are ultimately the customer, or can you say, you know what, this is kind of belt and suspenders. I don't need all this extra part in there. Can you explain?
Yeah, there's a lot to that. I'll start first with a little clarification on how it works. The plant, you are correct. The plant's default is, when in doubt, send it out, to the ocean. I'm a big believer in passive, fail-safe approach to things. Anytime you've got a control, an instrument, something that has to use computer logic, a pump, all that can fail. So I really prefer to use gravity. So it's really designed, if anything goes wrong, gravity flows to bypass, goes to the ocean as much as we can. In a passive way. That's why the safe diversion box actually is a passive diversion. There's control valves upstream of the fine screens that hold it to 1.88 MGD. Anything else passively spills over to the safe diversion system. You mentioned the safe settle tank. That was added during design after the bid had been selected. We didn't need it process-wise. The safe system did not need it functionally. It wasn't in the bid because this was a low price bid. They wanted the absolute, and they made it clear, the absolute lowest price possible was what mattered most to them, while still meeting the quality requirements and building a decent facility. So it wasn't in there. And that was one of the things that they wanted it for operational flexibility. They wanted it as a bit of a safety measure because, ultimately they are the operator. They're the ones who operators licenses on the line if they discharge, above permit. And so it was added. Oh gosh, I think it was after 60% design. So we had to kind of modify the design of that facility. And we came up with tacking it on to the sludge holding tanks. That's why there's actually 3 tanks there. It's tacked right onto the side of it. And it just happened to work that we can make it work by gravity and all that. So
does that then spill over to them as like a cost overrun or a change order because you had bid out? I think people are just
functionally, yeah. That's so in the fixed price design build delivery model, and there's fewer of these being done. Everyone's kind of going progressive. So progressive, you're doing this collaboration before there's really a GMP and a binding price. So a lot of those decisions happen before there's a price on the table. In this case, we had a fixed price that did not have it in it. We had contingency in there for risks that we carried. We had contingency in there for risks that the owner carries. And so they could dip into their contingency for owner selected changes, which they did use some of it for, but they also executed a change order to add that in there. And that's where that second GMP was really updating the contract for all their change orders. I'm trying to remember, our initial bid we ended at 80, and that was with other unforeseen conditions. There was a prehistoric landslide that no one knew about that showed up when we started doing excavation, had to be addressed, stuff like that. I think I think it was 72 million was our original bid, something like that, 70 million, somewhere in that range. So that was change orders added to the contract. So you still have change orders. They could have not done change orders, but a lot of those change orders were done to add value to the plant. The centralized chemical facility is another idea. We actually had totes where the chemicals were being ejected, because that's the least expensive way. They wanted it all in one place so they could secure it. That was for their insurance adjuster to lower their insurance rate. So to them, it made sense. It would pay itself in insurance.
Well, and that was, we had, as we're switching over now to some of these kind of permitting and thinking about the design build, one of the first questions we had, did the fixed price design build contract include contingencies for changes?
Mhm.
And you've just talked through that, right? So
Yeah.
one of the next ones that we had along this line, were the design bidders compensated in any way for their efforts prior to being selected? So is that just a lost lead, and sometimes you get it and sometimes you don't? So
Yep. No. Often they'll have they'll award you an amount of money if you were not selected, but that is way less than what was spent. Without revealing too much, but between us and Filanc, our total spend on this proposal was $1 million of overhead.
okay.
And you want to talk about getting executives in the room when you're like, hey, we want to spend $1 million of overhead for a project we don't have. Yeah,
Then
you're
we'll
having
bid on it. Don't
you're having
worry.
conversations with the CEO of a company of 13,000 people. Yeah, it's so it's a big deal to take one of these on, and that's where there's a lot of complexity to this. The owners need to understand what they're asking for to make sure that it's competitive and appealing for people to take that kind of risk. It's a big risk to take.
Yeah, no. And so how about, and then how about other environmental aspects, NEPA or other site work or all, so you were taking a new site. So was all that work built into the risk you were taking on, or was
Mhm.
that already
Yep.
managed for? So, okay, so you had all of that.
All the site drainage, SWIPy, all that stuff was all our risk to take. Yep.
Okay.
Permitting was complicated, like you said before. Really,
That's
it's
what I was
two
going to ask
plants.
you.
So you've got
Permitting, right? So you got
Regional Water Quality Control Board for the ocean outfall, and then you've got Division of Drinking Water for the IPR. IPR and DPR are new nationwide. California, Texas are really kind of ahead of the game on that. And so at the time this was being permitted, we were the first one to go in for the permit on MBR-IPR, and the regs are being written for AOP regulations and testing and proving. We actually helped set the standard for how that testing is done while we were doing the validation testing on our AOP system. So very complicated, but the state was good to work with on it. And when you're trailblazing, you're going to have a complicated path, and California never does anything easy. So
no, we get it. We get well, and some of the questions that came in while we've been discussing, people are like, okay, so you gave it, you are, you're trailblazing. You gave us some examples. You gave us some solutions you came up with, and some of the specific questions are like, so how about the brine in the future? Do you think I'm going to always be able to blend it back in and put it in my ocean outfall, or do you think that people are, I don't know. It's kind of crystal balling, asking you for some of those. Any ideas of things that were essentially allowed because you were one of the first, but maybe now folks are rethinking a little bit? Anything you can leave the audience with in that space?
it's an interesting question. As far as the brine to the ocean outfall, it's lower salinity than the ocean water. So actually, these ocean outfalls, part of the problem is it's fresh water, and that's a problem for the biology there in the ocean. So that blending and diluting it is a problem. So actually, brine is easier to blend into the ocean than typical wastewater effluent. So as far as Morro Bay and upcoming regulations that might impact them, no, I don't think so, because it was designed to be very proactive and ahead of the regulations. But we're chasing other projects. Brine is a big issue, and as far as where do you send it? If you're lucky and you're close to the ocean, well, then you do that. Southern California has a lot of actually brine discharge pipelines, and multiple agencies will gather together and chip in and share the cost of a centralized brine line that will send it off to the ocean. But if you're inland, now you're looking at other ways you have to get rid of it: evaporation ponds, higher recovery, which gets a lot more complicated really fast, a lot more expensive. So brine's a big one. As we move into DPR, that's going to get more and more complicated too. And then, the fact that the source water is becoming more and more concentrated is going to, I think, drive things as well, because it's making it harder and harder to get that squeeze.
Yeah.
Yeah.
So we've got, so as we're kind of, as we're kind of moving towards the wrapping up, right? So now let's think about this. So great engineering, great project, but eventually you hand the keys and now it's an O&M issue and somebody else has got to run this thing. And you've got an advanced wastewater plant and an advanced drinking water plant, lots of tech in a town of 10,000 that was already stretching itself to, to be able to put in this. How do you do that well? How do
That
you
is
that team
really the
to do
the
their
secret
job?
of the sauce. Is that how do you do that handover? Because that really can be a recipe for success or disaster.
Mhm.
Especially in this case, they went from a horse-drawn buggy to a, dual hybrid Polestar sports car.
You start with
Um,
a trickling filter and you end up with this.
yeah,
Yeah, different.
with it, night and day. And for the operators that did transfer over from the other plant, they were, pretty like, oh wow, this is super complicated. They love the new plant now because they're like, man, this thing is so much better and it's better designed and produces better water. But it was a big adjustment. Getting operators who have the certs to run a plant like this is a real problem. So, for anyone out there who's got friends or they're looking at their career aspirations, getting a grade 5 operator certificate, wastewater certificate in California, especially if you get the advanced treatment certificates, I mean, you write your own salary. They are so few and far between, and they're in such increasing demand. So what we did is we actually have operators in our, company, and we partnered with them and we worked side by side during startup. So they were involved in all the startup activities so they could see what they were starting up. They could validate the testing with us. You mentioned a question earlier about ethics of it. So maybe I can get into that if you want to. So they were side by side with us, helping run it. We were showing them each step of the way how to run it. We did a lot of training to take them through each system, how it works, work with them hands-on, and kind of do a slow transition from our operators running it to their operators running it and us supporting them and helping them as they, kind of get their sea legs and start running with it.
Sure. Well, and that's where you said like this next one's kind of like the ethics of that, right? So at some point in time you're handing it over to them. You're doing the punch card and yep, it all works, right? But if it's your own people, so if you design it, if you build it, if you start it up, if you operate it, how does that work for that actually handover where it's now a public utility? It's somebody else and it's their baby and they're doing it. How does that feel? How does that work when you're working in this very unique delivery space?
That's a question I've run into a couple times with it. And I understand why the question's there. But, there's checks and balances along the way. The owner had their own program manager who had a construction manager who was there every step of the way doing inspections. They were in the same trailer as us for a large part of it. And then they got their own trailer at one point when they had to expand. So they were checking that we were delivering what we showed on the drawings every step of the way. Ultimately, it's in our own best interest to do the best we can because we need a good reference and we do not want to end up in court. And, I think a lot of us in this industry, in this line of work, do this because we care. We care about the environment. And that's one of the things that matters more and more to me as I go further in my career. I've been at Black Veatch now 26 years. Doing something that is contributing to society and making the world a better place and supporting society in a positive way matters, I think, to all of us in this industry. So we want to do a good job. So you've got checks and balances with the owner having their representatives there watching every step of the way. And then honestly, the design build entity, as long as you're hiring a reputable entity, it's in their own best interest to do the best job they can too, so that they have a good reputation and don't end up in court.
It could get to build a future one for another because this doesn't gonna go away and stop. What a question
Yep.
that just came in was, was that part of the training and handover actually part of the original contract, or was that a separate piece? Or so is it's design, build, deliver. It's all the way through, right? So
all the way through. We did not hold operational responsibility as far as the state was concerned. So it was operated under their operational permits. But yeah, it was that startup and handover was part of the contract. I don't think it was very specific on exactly how it'd be done, but we know from experience. I mean, Black Veatch has been around for 110 years. I think 110 years now. We just know from experience that is key to do that correctly, or you're in for a world of hurt if the owner doesn't know how to operate the plant that they've just built.
Fair enough.
Yeah.
What's your advice? What's your advice for, we would have students, young professionals. We've got folks that maybe trained or went to school in the Midwest who are anxious to go out to California or go to other places where these places are a little bit challenging, maybe different than some of the things that they've experienced. What would be your advice to folks that are trying to follow in your footsteps or look to make moves or look for options to get in this space of thinking about direct and indirect potable reuse from a wastewater supply, right? So what would be your advice to those folks?
That's a good question. I've been actually talking to younger professionals about that lately. I mean, for me, I can just talk from the reference of my career experience. I started in Phoenix. That's where I originally grew up, and I was in our Phoenix office for 8 years, and it was intense. It was a boom cycle. Stick with your projects. I think that's the biggest thing, and it can be painful. I mean, I worked on Sac Regional. It was a 330 MGD wastewater plant, one of the largest in the country. I was the engineering manager for that. I was on that for 10 years, you know, but stick with it, because, you know, when you do this design, it's one thing to design something on a piece of paper. It's another thing to build it and then to operate it and then to work through the issues. And there will be issues when you're in startup. Startup is a very difficult time. Money is run out, time is run out, patience is run out. Everyone's tired and cranky. But getting through that, there's a lot more satisfaction, and you're a lot stronger of an engineer, and therefore you have more value. And then you get picked for the next project being an even better project. And then you kind of build up from there. So the biggest thing is sticking with it. And honestly, to be frank, younger folks tend to not stick with things as long. And I think they're really shorting themselves in that way because they're not learning everything. As far as
stick with it and grind it out.
Stick with it and grind it out, and all the way to the bitter end, because there's so much to learn from that process. If you don't do it, if you just do the drawing and then turn it in, and then you do the next drawing, and you never actually see through building it and starting it up and going through all those kind of painful processes, you're not going to learn how to be a better engineer, and therefore you're not going to learn how to move your way up in things. As far as opportunities, I mean, California is called the Golden State for a reason. It's expensive. It's very expensive to live here, but there's a lot of opportunity here too. Very strong market. So I've done well by moving to California. I remember buying my first house was a shocker, but you find a way. My realtor said, Eric, it's California funding money, and you just buy your house with California funding money, and then you sell it and you get more California funding money and buy another house with California funding money. I was like, that's not how math works, Benesia, but it kind of actually somehow does. So, you know, go to where the opportunity is, if that's what your career aspiration is, and stick with it and do your best to deliver good work and learn and grow, and you'll grow with it, especially where the market's growing and the complexity is growing. Yeah.
Excellent. Well, Eric, congratulations again to you and Katie and to Black Veatch for winning the 2025 Superior Achievement Award from the Excellence in Environmental Engineering and Science competition. We are so grateful that you were able to peel some time out and give us this fantastic webinar. This was just absolutely awesome. Thank you so much, Eric. Katie, we really appreciate having you here. We appreciate Black Veatch being a patron. We'll turn it over to Marissa to wrap us up.
Okay, thanks, Dan. And thanks everyone for all your questions. Thank you to our speakers for sharing your knowledge with us today. We have several webinars planned in the near future, so you can go to aaes.org/events and reserve your spot. Just a reminder, if you're not yet a member and you're considering joining the Academy, please email me to discuss our membership options. For all board certified individuals, PDH certificates for this event will be sent out by the end of the week. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.